Hello. This is Chapter 7. We're going to go over the review questions and the practice problems at the end of the chapter. So here we are at the end of Chapter 7. We're on page 248. 248. We'll quickly go over the review questions here. Okay, number 1. An object moves at a constant speed. Is the acceleration necessarily 0? Why or not? Or why or why not? Well, no. We know from circular motion that the speed, when an object goes around a circle, the speed is constant, is uniform speed, but the direction is changing all the time, and therefore for the direction to change, its velocity is changing. It has to have an acceleration. So, number 2, an object moves from point A to point B, and there's a curve that looks like this. Here's B and here's A. So, object moves from point A to point B. Along this path, and it has a red dot right here. Draw its velocity and acceleration vectors. Okay. Notice. Well, first of all, let's assume we're looking down on like this is a road. And we're looking down on the object and it's traveling along here. So if the object, at this point, for instance, the object's traveling this direction, that will be the velocity, but notice it's curving, and there's a particular, let's say it's a radius of curvature here through this little arc. So therefore, right at this point, it has to have an acceleration toward the center in order to pull it around the curve. At this point here, the velocity is going that way. That's the velocity. But the acceleration is like if we dotted this out, it's a partial circle. It's going in a partial circle, so there has to be an acceleration right to the center. Okay. Number 3. Given the force and velocity vector in like this, the force is this way and the velocity is this way, which will result in uniform circular motion? Well, the velocity is going this way, the force is directed this way, so this will lead to circular motion, okay, because in this case this force would be the centripetal force toward the center, and the velocity is at a tangent to that. In the B case, the force is going this way and the velocity is this way. Now, clearly what will happen is this object will definitely move. The velocity is going this way, the force is this way. Notice this angle here is less than 90 degrees, maybe only like about 45 degrees. Clearly, this object will be pulled in this direction, but is it going to be circular motion? No, it will not be circular motion. It will be some other curve, but it will not be circular motion. It will be curved motion, but not circular. Okay. Consider an object, let me write number 4. Okay. Consider an object moving uniformly in a circle. If the speed suddenly doubles, but the radius does not change, what new centripetal acceleration is needed to keep the object going in a circle? Okay, here's the object going in a circle. The acceleration is equal to v squared over r. Now the speed suddenly doubles. We were doing this, but now we're going to be doing 2 velocity whatever the velocity is, we double it, but then we have to square it. So that means that we have 4 v squared over r. So this is actually 4 times, if this is the old acceleration, this is the new acceleration. So the new acceleration is 4 times the old acceleration. Okay, so in order to keep traveling in a if the speed suddenly doubles, in order to keep traveling in the same circle with the same radius, the centripetal acceleration needs to increase by a factor of 4. Okay, because of velocity, you double the velocity and you square that, that means it's quadrupled. Okay, number 5. A student places 2 objects on a table, M1 and M2. This is number 5. They're real close to each other, a few centimeters apart. The student says that since the objects do not move toward one another, there must be no gravitational force between the 2 objects. Is the student correct? Why or why not? Well, he's actually not correct, and we know that. Even if they're on a table, like there's many objects that we have all the time that are close to each other, is there a gravitational attraction between these 2? Absolutely. Then why don't these 2 move together? Because of the friction. Because of the friction involved. So the gravitational attraction here is so small that any slight friction basically keeps them apart. It can't overcome the static coefficient of friction. And remember, a force needs to accelerate an object for it to move together, for them to move, but there's friction involved, so we normally only see this if we're working with big masses that are real close to each other. How can we ever see them attracted to each other? We only see it really in laboratory conditions where we remove the friction as much as humanly possible, and only then, when you're in laboratory conditions, kind of on a bench scale model, can you actually measure this force, because it's so small. Newton's third law. So, number 6. Newton's third law states for every action there's an equal and opposite reaction. Suppose 2 objects sit close to each other, just like this. The first object exerts a gravitational force. This is number 6. The first object exerts a gravitational force on the second object. Okay, what is the equal and opposite force that exists in the reaction to this gravitational force? Okay, the force of gravity, Fg, would be g m1 m2 over r squared. That's the force that's attracted m1 to m2, but it's also the force that attracts F2 to m1 to m2. So, and they're equal and they're opposite. Okay, does that mean necessarily that these 2 objects will accelerate? Assume there's absolutely no friction. Will they accelerate the same? No. They will only accelerate according to their inertia, either m1 or m2. Hope that's clear. Okay, number 7. Let me erase some of this. Number 7, you have already been told that the acceleration due to gravity is not really constant near the surface of the Earth. It varies a bit depending on where you are. Compare the acceleration due to gravity at sea level, say right here, this is the Earth, and here's the radius, say that's the center. That's sea level to another place where you have a mountain, say at the top of Pikes Peak. Where do you expect the acceleration due to gravity to be greater? Well, first of all, assuming, well, we know the force of is G-M, Earth, and this is the mass of, say, U, divided by R squared. Okay, what's the mass of the Earth and the mass of U is the same. Everything's the same, but what is different is the radius, of course. Now, so the first answer is this. The first answer is this. We have R1. Here we have a little R2. This little increase of, because of Pikes Peak, increases R2. So since R2 is greater than R1, that means the force of gravity at 1 will be greater than the force of gravity at 2. Okay? If I put a larger number into the denominator and square it, it's going to give me a smaller gravitational force. Okay? All other things being equal. And that's the key to this problem, assuming that the mass is the same. Now, in reality, what is the other factor? The other factor is, when I talked about this before, is actually the local density of the Earth in this immediate area versus the local density of the Earth in this immediate area. The local gravity not only changes because of distance to the Earth, but also the density of the rock between you and the center of the Earth. That also has a large impact also. Okay, number 8. Two objects are in close proximity to each other. If the distance between them suddenly doubles, what happens to the strength of the mutual gravitational attraction? Okay, if this distance suddenly doubles, then we would have, if this is number 1, if we say, if we double the distance and square it, we end up with 1/4. If we double the distance, we end up with 1/4 the gravitational force, because the distance is squared, so when we square the 2, we end up with 4, but that's 1/4, so the gravitational attraction is reduced by 1/4. Well, yes, is reduced. Actually, it's reduced. It's reduced by multiplied by 0.25. There we go. Okay, number 9. An annoying fly traveling around your head in a circle. If the fly suddenly increases its speed but stays in the same circle, does the orbital period increase or decrease? If the speed, here it is, it has a certain velocity. Okay, it's traveling in the same circle, but it increases its speed. When it increases the speed, it goes around a circle faster, so that means its period gets smaller. The period gets smaller because it's traveling faster. If the period gets smaller, then that means that the frequency, which is 1 over the period, gets larger. The frequency, the number of revolutions per second. Okay, and number 10, in the spin cycle of an automatic washing machine, the clothes are spun around inside the machine at a high rate of speed. Okay, here you're looking at the top-down version of your dryer. Clothes are spinning around this way, and what happens? They're thrown to the outside of this big drum. Now, This removes a large amount of water that is soaked into the clothes. Given the fact that the walls have small holes in them, explain the physics behind this. Well, when the clothes are thrown to the outside, the water is thrown to the outside too, and the clothes will not go through the holes are too small, but the water droplets can, and so the actual water droplets get thrown. Anything that can move beyond this will, if there's nothing to hold it back, so water is actually thrown to the outside. Okay. If you had a if there were no holes, the water would not be able to leave the clothes, and so the water would just spin around, staying with the clothes, i.e. the clothes to still stay wet. Okay, that's number 10. That's the review questions. Now we're going to go to the next page, page 249, to the practice problems. Okay. Okay, number 1. An airplane pilot nosedives and then pulls his plane upward, forming a semicircle in the air. Here's his center, and he's kind of doing this kind of thing with a certain radius here. The radius is 112.2 meters, and his plane, the mass of his plane, is 455 kilograms. Okay, and the plane's airspeed is 73.3 meters per second. Question is, what is the centripetal force on the plane? Well, the centripetal force is mv squared over r. So this is just a direct substitution into this. So we simply substitute into this, and then we get 455 kilograms. We substitute the velocity, 73.3 meters per second, and we square that, divided by the radius, which is 102.2 meters. And let's see, we get 73.3, we square that, times 455, divided by 112.2, we get, I get 21788 newtons, but we have to round that off to 3 significant figures, so it would be 2.18 times 10 to the 4th newtons. Okay? Okay, number 2. A popular amusement park ride is made up of a hollow cylinder that spins. And you've seen this before. Maybe you've even ridden on one. I have many years ago. This thing spins around. You're an amusement ride. You're standing here, and it spins around real fast, and then sometimes they'll even drop the floor out. I don't know if they have this ride anymore. It may be considered too dangerous, but I remember as a kid doing it. And maybe they weren't as safety conscious back then, I'm not sure. But, okay, so let's see. The question is, you have a radius of 5.1 meters. And the question is, how much centripetal acceleration do the riders experience? Okay, well, acceleration, centripetal acceleration, is v squared over r. And, oh, that's right. The velocity they give you is 15.1 meters per second. So again, that's just a straight application, just plugging directly into here. It's 15.1 meters per second. And then we square that divided by 5.1 meters. And notice one of these will cancel out, and we'll get one of these meters will cancel out. 15.1 squared divided by 5.1. And we get 40, rounded off at two significant figures, 45 meters per second squared. Okay, so that's the acceleration, and obviously the acceleration, your acceleration has to be directed. The acceleration is directed to the center, but actually what do you feel? What you feel is the centripetal acceleration throwing you back, right? The centripetal acceleration throwing you back, that's actually what your body feels, but it's fortunately you feel that, you feel the wall, and it's a good thing you felt the wall, because if you didn't feel the wall, you'd just go flying out. So the wall, the rigid wall holds you, and because of friction, you don't fall. Because why don't you fall? You don't fall because of friction. And so even though you feel thrown back, the wall is rigid, and it is strong enough to supply the acceleration right to the center. Okay. Okay, number 3. Okay. A child attaches a 34.5 centimeter string to a 15-gram ball and begins to twirl it around his head. He twirls it faster and faster. Eventually, the ball reaches a speed of 12.1 meters per second, and then the string breaks. What is the maximum tension the string could withstand? Well, the maximum tension happened right when the ball reached the maximum speed, and then the string breaks. So the centripetal acceleration is mv squared over r. Again, I'm not going to solve it, but that's just a straight application of, again, this v squared over r. You put the mass in here. Now remember, the mass is 12 grams, but we have to convert to kilograms, so that's 1 kilogram divided by 1,000 grams, 0.012 kilograms. So remember to convert to kilograms. Then you plug this in, plug in the radius. Again, the radius is 34.5 centimeters. Convert that to meters, 0.345 meters. You plug that in, and you should get an answer that's 6.37 newtons. That's the maximum strength of the string, the maximum tension that the string could withstand. Okay, that's number 3. Okay, number 4. This is number 4. A car is traveling down a slippery road, and it gives you the coefficient, the kinetic coefficient of friction. We'll assume it's kinetic because it says it's traveling, of 0.22. What is the maximum speed at which the car can take a flat road whose radius of curvature is 13.4 meters. Okay. If you can picture this, you have a car. We're traveling around the car is traveling around in a circle. Okay. It's going a certain speed. And in order for the car to travel in a circle, there has to be a centripetal acceleration and a centripetal force right to the center, as we know. Okay? Now, what supplies the centripetal force to allow it to, what supplies the centripetal force? Well, it's the contact of the wheels with the road. So if I look at a side view of this, here's the car wheels. These are the two car wheels, and the car sits on top of this, like there's the car. The car is traveling around that way, and so there has to be a centripetal force this way. Well, what supplies that? What supplies that is right here, right the contact between the wheels and the road. If this road was pure ice, absolutely no friction or very little friction at all, the car wheels could not grab the road, and you would not be able to turn because there's no friction, no force no frictional force can be turned into centripetal force toward the center. So basically, it's the frictional force here. This friction between the wheel and the road is what allows what is essentially that gives this force it gives the centripetal, it supplies the centripetal force. Okay, so the friction essentially supplies the centripetal force necessary to move around in a circle. Okay, so the friction here, remember the friction is the coefficient of friction, the static one, times the normal force. Remember the normal force, in this case, the normal force is equal to the weight. The normal force is equal to the weight, which is mg. Okay, so the friction force is a coefficient, kinetic coefficient, times mg. Now, this friction also supplies the centripetal force necessary to move it in a circle, mv squared over r. Okay. Notice that the mass of the car cancels out. The two masses cancel out. Okay, and we can go ahead and solve for r. So we're going to multiply both sides by r times r equals v squared. So the square root of the coefficient times g times r is this velocity. In this case, it will be a maximum velocity that could potentially, the car could have the maximum velocity of this. If the car went faster than this, then this term over here goes higher than can be the friction can that the friction can supply, and so what happens? The car essentially is thrown out of the circle. It can't withstand that amount of acceleration, that centripetal acceleration, so it leaves the circle. It has to. So you try to keep it in a circle if you exceed that velocity, but the friction won't allow it, and you would end up going out of the circle like this. You may still arc, but it won't be a circle. So what is that? Let's go ahead and plug in here. to find out what that maximum velocity is. So the maximum velocity is 0.22 times 9.8 meters per second squared times the radius of 13.4 meters and all square root. Now notice we have meters times meters squared divided by meters, so second squared. So when we take the square root, we'll end up with meters per second. So 0.22 times 9.8 times 13.4, and then take the square root, and I get 5.4, rounding off to two significant figures, 5.4 meters per second. So that will be the maximum velocity that car could go, and still maintain a circular pattern. Okay. On to question number 5.